Welcome to this edition of Horner Automation Tech Tips. In this video, we're going to be looking at setting up a PID function. Before we add the PID function, you can see that I have some logic already in here. There's a scale function. This is used to upscale the set point data to a raw data range of 0 to 32,000. And we've also got a move block that is going to take an analog input and move it into the process variable. And then at the end, we've got another move that is going to take our PID output, our CV, and move it into an AQ, analog output register. You can see that I've got always off contacts in front of all of these. That's because I'm not going to do this demonstration with any real world I/O, so I have these turned off. These are additional rungs of logic that you would be using with the PID function. Also, before we get into the PID function itself, we're going to look at some program variables that I've already set up. First, we'll look at the retain variables. We've got the SP, our set point, and we have the PID block, and the PID block uses a structure called PID. In that PID structure is all of the parameters and settings that the PID uses to operate. So let's look at our global variables. You can see that we have a lot of built-in variables in Cscape. These just come with the program automatically. I'm going to scroll down, and now we can see some of our variables that we're going to use for the PID function. We've got our PV for process variable. I'll scoot this program variable table off to the side here so we can see the logic. So you can see we have an analog input going into our PV. And then we have our CV, and our PID output is going to be going into an AQ or an analog output. And we've got a manual enable bit, a manual up and down bit. And then rounding this all out, we've got our start auto-tune bit and auto-tune done bits. So in the project toolbox, we can see that we've got the listing about halfway down, PID operations. We're going to select a independent PID to use for this demonstration. So let's go ahead and fill in our PID function. We've got the PID underscore block. Again, that was the variable that was set to structure. You can see all of our structure variables there, sub-variables to the PID block. So we'll select that, click our green check mark, and then you can keep adding things from the list of variables that you've already created, or you can just type these in. We're going to add our PV and add our CV variables, and then I'm going to select these from the list. This is going to be our manual enable, and then manual up bit and manual down bit. Now we're also going to check the box for support auto-tune, and I've got variables that I created for that as well, so we're going to select those out of the list. We've got our start auto-tune bit, and then we will select our auto-tune done bit. For this demonstration, we're going to tune for P and I. You can see that we've got selections there for P, I, and D for proportional only. For this demonstration, I'm going to select PI to tune. And since we're trying to keep this video short, I'm going to leave the rest of these set to default. So let's OK out of this. And we're going to look down at the status bar at the bottom of Cscape. You can see down here that we've got an XL4 prime connected to Cscape. We've got local 253, which means we're connected. We've got target 253, which means that's the one that we want to watch. And we've got R run for run and no forces. Let's go into our PID function, and we're going to click on this tune button here. Now this window only means something when you're connected to the controller. When you launch this tune window, Cscape goes out and gets the values from the controller and populates them into this window. And then we've also got a update controller at the top. So when we make edits here, we can update the controller and send the edits that we've made to the controller. And we've also got a save set points option here that you can save your settings to a set point table in Cscape that stays with the program file. So you're going to see a few values in here. Our PI and D are currently at 0. And we've got a sample period of 100 milliseconds. And we've got a upper clamp set to 32,000. The upper clamp is one of those gotcha parameters. I will get calls sometimes, people doing PID, and they tell me that they've got everything set up, but they're not getting any output from the PID. And one of the first questions I'm going to ask is, what is your upper clamp set to? And very often, the answer that I get is my upper clamp is 0. If you have a 0 for the upper clamp, you're telling the PID function that it can't put anything out greater than 0. So that's obviously not going to work. So generally speaking, we want to have a 32,000 in here. There might be some situations, some applications where you want to limit that and put a lower upper clamp there. But generally speaking, you want the full range and set that to 32,000. Okay, we've got the parameters where I want them for now. We're going to close out of the tune window, close out of the PID function, and we're actually going to go away from Cscape and open up a WebMI page that I created for this demo. You can see that we've got the XL4 prime here. We've got the PID function running in the XL4 prime. We have a set point entry, and we have our CV over here on the right. Going out of the controller, that's going to be a 4 to 20 milliamp out or a 0 to 10 volt out, or it may even be a digital output if we have the PWM output. So the CV is going out to our process, which is whatever your process is. It might be temperature or speed, etc. And then connected to that process, you're going to have a sensor, and that sensor is going to provide our process variable, our feedback to the loop. So the PV from the sensor comes in to the controller on the analog input and gets put into the PID function, and then that closes our loop. So right now, our output is 0 because our process variable equals our set point. I'm going to give it a proportional value of 1. We still have a 0 output because the process variable equals the set point. So we'll just make a little change here to the process variable, a slight change. I'll put in a 499 there. And you can see that our CV is 1. The CV is 1 because that is literally the difference between the set point and the process variable, and our proportional term is set to 1, which is a unity gain. So whatever the difference is between the process variable and the set point variable, that's what's going to be put out on the CV. So we'll show this slightly different. We'll put a 2 in here for the proportional term, and you can see our CV went to 2. So our difference is 1 times 2 is 2 on the CV. So if we put a 490 in here, that's a difference of 10. 2 times 10 is 20. So our proportional term is 2 times 10. We get 20 on the CV out. So let's add some integral. Now we can see that the CV starts to climb. It's trying to push that process variable up to meet the set point. In a real world, our process variable would be climbing, but I'm doing this manually. So let's change this PV. We'll kind of bump it up here, and we can see how that affects the CV as that comes up. Now we're only 1 off from the set point, 1 raw data count away. The CV continues to climb, but it's climbing at a much slower rate. The integral term builds value over time. So right now the CV is not moving because the PV equals the SP. So as far as the PID loop is concerned, it's maintaining that process right where it's supposed to be because the PV is equaling the set point. So let's switch gears and look at the auto tune. I'm going to change this process variable to 450 to make it a little bit more like a real world situation. You want to have the process variable close to the set point when you start an auto tune. If the process variable were at 0, it would take a long time to get up to the set point, and that would throw off the tuning a little bit, and then you would end up having to redo the auto tune. So whenever you start the auto tune, you want the process variable to be fairly close to the set point. The way the auto tune works is it goes through a min-max cycle on the control variable. It sends the control variable all the way high, all the way up to 32,000, and times how long it takes the process variable to go past the set point. Once it goes past the set point far enough, then the control variable goes all the way down to 0, and then it times how long it takes the process to go down below the set point by a certain amount. So we start the auto tune. You can see that the control variable went all the way up. And right now, the process variable in the real world would start to climb. So let's go ahead and start doing that. The process variable is going to start climbing because the control variable is all the way up. And once we get far enough past the set point, then the control variable is going to go all the way down to 0. And then we wait for the process variable to go down. So the process variable starts coming down, and once it gets down past the set point far enough, then the control variable goes all the way high again. And we had just completed one cycle, so we got 2 more cycles to go. Control variable is all the way up, so the process variable starts going up. We get far enough past the set point, now it goes down to 0. The process variable starts to come down. We repeat the cycle. Now we just finished 2 cycles, one more to go. Process variable climbs. And once it gets far enough past the set point, then the control variable goes down to 0 again. The process variable starts to fall. Once it gets down below the set point far enough, the done bit is going to come on and the PID will start controlling the loop. Okay, so you can see that the control variable is very active now. Our D term is 0 because if you recall in our setup earlier, we selected only P and I. The auto tune gave us P and I settings to work with, and the loop is active. And from here, we'll just let this process variable sit here at 500. Again, I don't have anything hooked up to the controller. I'm just simulating this process variable. One last thing about the auto tune is that the done bit you can see is still on, and the auto tune start is still on. It is up to you on how you want to turn that off. The PID function does not automatically turn that off for you. So either an operator is going to turn it off from the screen, or you could even build some program logic to turn that tune bit off automatically. It's entirely up to you. One reason that you might want to do it the way I'm doing here is because that done bit stays on, and you can see that an auto tune has been performed. With that, that is the end of our video. There's lots of other items to cover in a PID loop. We have more comprehensive videos on our website, so if this video didn't answer your PID questions, check out those other videos on our website. That's it. Thank you very much.